All right, so looking at our proposed reaction mechanism, right, we can actually write the rate laws for this reaction. Okay, so what I'm going to do is I'm going to label this as step 1, and this is going to be step 2. Okay, and what we can do is for each step, we can write the rate law. This is totally different than our observed experimental rate law. With our observed experimental rate law, right, we couldn't just use the coefficients of our molecules to write the rate law. But with our elementary reactions, we can use our coefficients. So for step 1, my rate of step 1 is going to be equal to K1, right? We always have K there. And then it's going to be the concentration of NO2 times the concentration of NO2. Well, that's really just equal to K1 times the concentration of NO2 squared, right? So this is the rate law just for step 1. And then we would have a rate law for step 2. So our rate for step 2 would be K sub 2, right? I'm going to use K sub 2 to be my second step. And then it's going to be CO times the concentration of NO3. Now, if we experimentally measured that our rate law was, so rate EXP was equal to a second order with respect to NO2, well, that would fit with our proposed reaction mechanism that says that this is our first step and maybe this is the slowest step. Okay? But we don't always have reaction mechanisms where the first step is the slowest step. Okay? Sometimes we have reactions where it has to go through a step, get an intermediate, and then go through a slower step. Okay? And that's where we have to use this steady state approximation. Okay? Yes, this is an approximation, but it turns out that it's generally going to be pretty valid. Because if we think about our multi-step reaction energy profile, right? Let's draw what we had before. We've got our energies here. Maybe we have our reactants that goes over one pretty small hump pretty easy, right? And then it has to go over a higher hump, and then it will go to our products. Well, for it to get over this second hump, it's going to be able to be going back and forth between our reactants and our intermediates, and products. Reactants, intermediates, and products, where we're going to be able to go in between our reactants and intermediates fairly easily, especially in comparison to our molecules that are actually going to be able to undergo the reaction over to our products. So our steady state approximation basically says that we have a constant amount of our intermediates. Okay, if our highest peak here is after our intermediate, okay? And so this would happen, like I said, when one of our steps, our slowest step, our rate determining step, or RDS, the rate determining step, if it is the second step or if it's the third step, right, we're going to have intermediates that are going to be there before, okay? So what I'm going to do is this would be a possible energy profile if we had a second step that was slower than the first step. So what I will do is let's look at another reaction. If I were to have, so we're going to do step 1, we're going to have NO gas plus Cl2 gas. It can react and form NoCl2. It's pretty easy. So we're going to have an equilibrium here. Okay, so we're going to have a forward reaction and a backwards reaction occurring. It's pretty fast. Our second step, step 2, we're going to have NoCl2 and NO, and that's going to produce 2 NoCl. So our overall reaction is going to be 2 NO plus Cl2 goes to 2 NoCl. Okay? So in this case, right, we would say the rate, so I'll do rate 1 for step 1 is going to be equal to K1 times the concentration of NO times the concentration of Cl2. Then I have my rate 2, which is going to be equal to K2 times the concentration of NoCl2 times the concentration of NO. Okay, so if I do this, now I realize that, oh, my reaction here, my rate, this is my rate limiting step, my rate determining step, has NoCl2 concentration in it. But whenever I experimentally measure the rate, we're never going to have NoCl2 in that reaction because this is an intermediate. We never know the concentration of this intermediate. So for me to evaluate this reaction mechanism, I need to remove this intermediate so that I only have my starting pieces in my reaction. Okay? So what I can do, though, is I can say, well, my NoCl2, right, it came from this first step. So I can write another rate where my rate minus 1 is going to be equal to K minus 1, where we're going from this first reaction, we're going backwards, and it's going to be NoCl2. Okay, so if I have this rate here, because it's an equilibrium, my forward rate and my backwards rate are going to be equal. So I can set my rate 1 forwards rate and my rate 2, or sorry, my rate minus 1, my backwards rate, equal to each other. Okay, so, whoops, I'm going to do small k 1 times NO concentration times Cl2 concentration is going to be equal to K minus 1 times NoCl2. Then I can solve for my NoCl2, right? That's what I wanted to get rid of in my rate 2 expression. So I will divide both sides by K minus 1. And now I know that my NoCl2 concentration is going to be equal to K1 over K minus 1 times NO concentration times Cl2 concentration. And then I can take this and plug it into my rate 2. Okay? So this was my slow step, again. So I needed to write the rate expression for that slow step. I had NoCl2, which was an intermediate in it. I don't want that because I don't know those concentrations. I set my forward and my backwards reaction of my first step in there, and I solve for NoCl2. Now I can take this, plug it into my rate 2 expression, and evaluate that rate. So my rate of my slow step that I want to compare to my overall experimental rate is going to be equal to K2 times, oh, I have NoCl2 there. Well, let me come down here. Well, this is K1 over K minus 1 times NO concentration times, oh, I'm off the page, times Cl2 concentration times my NO concentration. Well, this would be NO squared. So now I can evaluate this and say, right, is my overall rate that I looked at, that I measured in the lab, I've got some K value, and then it's going to be, whoops, not equal, times NO squared times Cl2. And I can evaluate and say, is NO second order? If in my experimental measurement of my reaction, is my rate law, does that have NO concentration squared? If it does, and it has Cl2 as a first order reactant, then I can say, well, this mechanism is a plausible mechanism for that reaction, okay? So that is really what we want to be able to do, is we want to be able to evaluate our rate laws and see if we have this mechanism, does that mechanism fit with our experimental rate law based on the math that we do with those rate laws, okay? So then our last piece here is about our catalysis, right? A catalyst, all it is going to do is it changes the reaction pathway. And when it changes that reaction pathway, it lowers the transition state. Okay? It finds a new way for us to go through this reaction, and that reaction is going to have a lower transition state energy. Okay? So our mechanism, our energy diagram, basically would just bring this step down. Okay? All right. So now we should be able to do a whole lot more problems.